Hello again and welcome. Oh, sorry.
Do you want the sound off here?
Please. Thank you. Sorry. Hello again and welcome to the A4Q Testing Summit, streaming live from Marrakesh. In this session, we have Chief Technology Officer at STA Consulting, Dr. Stuart Reed, with nearly 40 years of experience in the IT industry, working in development, testing, and education, is here to share with us his expertise around the topic testing in AI, a new testing specialism. Stuart, if you're ready, the stage is yours.
Okay. Okay, I carry on. Okay, so what I'm going to talk about this evening here in Marrakesh is how I believe that we're going to require a new test specialism in testing AI as AI is becoming more important to us. So first of all, what I want to first to do is talk about the importance of AI. As we can see from the first bullet point, the worldwide AI market is predicted to exceed $500 billion. That's over 5,500 billion Moroccan dirham by 2024. It's a growing trend. In 2021, 56% reported some AI adoption, up from 50% in 2020. And 92% of businesses report their increasing investments in AI and data. So 26% of companies already have AI systems in widespread production. And it appears that large organizations are leading the way here, with 92% already achieving returns on their AI investments. AI and machine learning are the top IT investment priority in Europe at the moment. So it's going to be big. If it's going to be big, do we trust it? Well, people think it's going to change their lives a lot, and it changes across countries, as we can see here. Globally, 60% believe that AI is going to profoundly change their lives in the next 3 to 5 years, although this varies widely. So places like Germany, places like the UK are in the mid 40%. But if we then move to the Far East and look at the belief there, we have Korea at 76% and China at 80% believing it's going to change their lives. It will change our lives, but by how much depends on how much we're going to share our information with the systems. So even though 60% believe it's going to change their lives, only 40% actually want to share their information with an AI system. And a third of the people don't actually trust any recommendations or decisions from the AI systems. If we look at the figures though, what we actually find is that many people aren't actually aware that they're using AI already. So only 41% of people using social media are aware that it's using AI. So if we were to actually make those people better informed, we'll probably find that more people are going to have problems with sharing their information. Across the globe, 50% of people trust companies using AI as much as they trust other companies, which is right in the middle there. However, again, it changes as you move from Europe to the Far East. In the UK, 35% trust companies using AI as much as they trust other companies. So in the UK, not much trust of companies using AI, whereas if we move to the other end of the scale, over 3/4 of people in China trust companies using AI. So in China, there's more trust of AI companies than normal companies, whereas the opposite trend in Europe. So how do we actually look at this trust specifically? Well, if we look, what we find is that where the AI is doing really complicated stuff, such as healthcare AI, and this might be because we don't understand what the AI is doing, they will trust it to do that. But if we feel we could do it ourselves, so human resources AI, then people are not willing to trust the AI to do that as much. On the other hand, 57% will be willing to use AI if the insurance mechanisms are put in place. So from a testing perspective, there's a big opportunity here. If people are going to trust AI, they've got to have these assurance mechanisms. So if we test the systems enough, maybe the people will trust them enough. One of the reasons people are wary of AI is because they believe it's going to take their jobs away. As with previous industrial revolutions, people are worried about their jobs. If we look at it from a government level perspective, and we look at what the World Economic Forum predict, they're predicting 85 million jobs are going to be lost to machines by 2025. But on the other hand, they believe that 97 million new roles will be created by AI. So actually, there's a net gain for people there. And in fact, if we were to look back at previous industrial revolutions, this has always been the case. People believed that their jobs were going to get lost, but in fact, more jobs were actually created. But those are figures from the top down. These are government type figures, large organization type figures. If we actually look at the individuals, only 22%, so only just over a fifth of people actually believe that. And most people actually believe that jobs will be lost to AI systems. Most people are happy for AI to take over their really boring tasks, but they don't want the AI to do the decision making, such as evaluating employees. If we actually look at the jobs that are associated with AI, then actually data scientist was the second best job in the US in 2021. And when we're measuring how good a job is, what we're looking at is not just that it pays the most money, but that it has it's enjoyable, that there's enough jobs so that you can find a job. So data science seems to be a really nice area to work in. And in fact, if we look at the LinkedIn, we find that AI specialist was the fastest growing job category in 2020. The fact that it's AI specialist is this growing job category. One of the specialisms within AI is testing. And so what I want to take you to look at is this AI test specialist role. So if we were to go back in time a bit, not many years, we're in the situation where we've got the data scientists developing AI and machine learning systems. And they're building the whole systems themselves. So what we can see is the data scientists are bringing in lots of AI, machine learning knowledge, and very little testing knowledge. And I've deliberately just put it as AI and machine learning development because very little testing was being done. As there were a number of failures, as the lack of trust became more apparent, testing became more important. And you can see that the data scientists then started doing some testing. As they started doing some testing, They were using some testing knowledge, perhaps from that they'd learned in other roles, and they were using generic test techniques. My hypothesis is that we're now moving into this third stage. And in this third stage, you can see at the bottom there is a specialist testing role. And so with this specialist testing role, the data scientists aren't doing the testing. We're actually getting specialist testers in there. The specialist testers, to be able to test AI and machine learning systems, have to know something about AI. So you can see that they're bringing in some AI and machine learning knowledge, but mostly they're bringing in testing knowledge. And the other thing you can see is that the testing knowledge now is not just generic test techniques, but we're bringing in specific AI testing techniques. And what I'm going to show you over the next few slides is what I believe some of these techniques that are going to be required and how they're different from conventional testing that we're used to. So first of all, what I want to do is, for those of you who aren't completely familiar with machine learning, actually show an abstract model of how machine learning works so that you can see where the testing might fit into this. So if we're going to build a machine learning system, the first thing we have to do is understand the problem, as we have to do with any system. The difference with machine learning is it's very dependent on data. So I'm going to use data-driven systems as the example here, which is the vast majority. So once we've understood the problem, we select the data that our system's going to use. The data is typically going to be in a form that we can't use immediately, so we're going to have to prepare the data. And in fact, the preparation of data for data scientists is the biggest task in building a machine learning system. That gives us the development data. It's machine learning, so we need an algorithm to actually work with the data. So we have to select an algorithm. There are lots of algorithms to choose from, so a large part of the skills of a data scientist are knowing which is the right algorithm to select. We then acquire the algorithm, and now we've got development data, we've got a machine learning algorithm, and we're going to actually let the machine learning algorithm play with the data. This is why it's machine learning. There's no programming involved here. And the machine learning algorithm builds the machine learning model. So this is our second step. Now we've got machine learning model, we can actually put the model on the web and people can use it as a service, or we could embed it as part of a larger system. So in step 3, we move to operation, and now we've got a machine learning model. It needs production data, which needs to be prepared because it requires data in basically the same form as we needed the training data or development data earlier. So we prepare the data, the machine learning model takes the production data, typically observations of the world, and comes up with predictions. And that's our 3-step process. If we show all 3 steps together, what we can see is what we've got on the screen now. And from a testing perspective, what we can do is actually break this process into 3 different areas. In the first, which is called here input data testing, this is concerned with the data that we use for machine learning. We've got the framework testing, so the actual algorithm, which works as part of a development framework, needs to be tested as well. So we need to make sure that we choose the right algorithm. We may need to make sure that the algorithm is working correctly. We need to know that the development framework in which we're using to actually build the system is working correctly as well. And finally, much closer to traditional testing, is our model testing. This is where we're actually testing that the delivered model is doing what we want it to do. And we can see we've got some overlap there. The production data is going to be covered both by the input data testing and by the model testing. So what I'm going to do next is actually go through each of these three areas and explain how they work in slightly more detail than we've got there, to give you some idea of why we need to test differently, and then show the different defect types that we get with each of these three areas. And from the defect types, we can then move to looking at the test types that we need to actually find those defects. And we can see, ideally, how that differs from conventional testing. So starting with the input data testing, how does it work? Well, we start with raw data. And one of the things we use when we're building machine learning models is we use data pipelines. So to transform that raw data into a form in which we can use and pass to the algorithms, we feed it through the data pipeline. And what the data pipeline is doing is taking the data, it's cleaning the data, it's looking for missing values and maybe replacing those missing values. It's putting it in the right format that we need it for the algorithm. As I said earlier, this preparation of the data is the biggest task that the data scientists perform. As you can see, we have two data pipelines. The first data pipeline is for when we're training the models, and then the second data pipeline is for when we've got the model in its operational environment. Once it's in its operational environment, the production data pipeline is going to be fully automated typically, because we'll be running this perhaps every few seconds. So we can't do it manually. Whereas with the development data pipeline, we'll be doing trial and error to do different data preparation until we get the data into a form and we select the right data to get the best results from our machine learning. So the development data comes in three forms, and they may overlap on the left, although the test data is going to be completely independent. So the training data is going to be used to actually train the model. The validation data will be used to check that the trained model comes up with a reasonable accuracy. And then to make sure that there has been no problems with that, we have a completely independent set of test data to make sure everything's working okay before we move to production. The actual data pipelines, especially the production data pipeline, need to be designed and implemented, and it's software. It's just a standard software engineering project, in which case the software testing is conventional software testing of those. So if we look at the development data pipeline, what we can see is typically we've got up to three particular activities we have to perform on the raw data to get it into a form that's usable by the machine learning algorithm. So we've got data acquisition, we've got data pre-processing, and feature engineering, where we decide which of the features in the data are of particular interest to us. There is actually an option of not going through that, because that takes an enormous amount of time and is highly skilled, and it's why we call data scientists. And they're expensive people. So one of the options instead is that we can acquire pre-gathered data sets and use those instead. So what sort of defect types do we get? Well, you can see lots on the screen here, and we haven't got time to go through each of these. But one of the things you can see is that, for instance, unrepresentative training data up there on the top left, from the tester's perspective, what we're trying to make sure is that the data going into the training is fully representative of the data that's going to be used in the real world. This requires, obviously, our testers to have full knowledge of the application domain in which the machine learning is going to be used. Moving below that to bias training data, one of the problems we get with training data can be that it's biased. It might be biased in terms of gender, it might be biased in terms of race, and systems have had lots of problems in these areas. And this is a specialist type of defect that we only get with machine learning systems, because the bias comes from the data and where we collect it. And it's historic data. And if historically we had bias, then by using that historical data, we train it into our machine learning model. And of course, we don't want to do that. On the right-hand side, we can also see some more simpler things for testers to find. We've got missing data there or wrong data types. It's really easy to see how you would find missing data, because you're just going to look for fields that are empty. Wrong data types, well, if you're looking for numeric values and you can see strings, again, really easy to test for. So if we've got those defect types, what testing types do we need? And on this slide, you can see we've got a range of different testing types. For instance, let's picking one there, we've got on the right-hand side, feature contribution testing. So what we're looking at there is how each feature in the data contributes to the accuracy of the results in the model. So you could imagine we're looking at a facial recognition system that is maybe for passport control, immigration control with passports, and the feature contribution testing might be looking at perhaps we look at people's eye color, and it's expensive to get the information in, and how much does that actually increase the accuracy of the model? And we might decide that the cost is too high and that feature isn't contributing enough. We've also got their unfair data bias testing, and what we're looking at there is things like race and gender, and is our system actually biased, perhaps against women, perhaps people of a certain race. And if we look at the yellow highlighting, these are all the testing types that are specific to machine learning. So of all these input data testing types, you can see that it's only data governance testing, which isn't a specific AI or machine learning type. So these are all new things that if you're a conventional tester and you want to move into AI testing, these are all new types that you're going to have to become familiar with. Although, of course, as with all testing, you don't need to know, and you wouldn't use every testing type on every project. What you can see here is data from a 2021 survey, and this 2021 survey was a really large survey, and it's showing what is actually happening in the world today. And what you can see is that only 40% of organizations are actually checking for underrepresentation of protected characteristics. By protected characteristics, we're looking at race, gender, etc. So that means that 60% are not actually checking that their system isn't unfair, which seems really strange given how bad the publicity is for machine learning systems in the press, and probably contributing to the lack of trust that we're getting in the figures that I showed you earlier. Only 37% check that the raw data isn't skewed or biased, and that might be because the raw data is being gathered from data sets which perhaps don't look at people over the age of 50, but only look at younger people. And 30% only check that the machine learning workflow isn't actually causing a problem itself. So we might cause bias in the machine learning workflow for instance, but by simply just not randomizing the data before we select a sample. And by not randomizing, it means we're only collecting from maybe the top 10%. And if it's an ordered set of data, that then gives us a particular set of bias. So moving on to the framework testing. So this is to do with the selection of the algorithm and how we actually build the model from the data using a development framework. So once we know what the system's going to do or needs to do, we can select what we feel is an appropriate algorithm. Then we actually do the training. So the training's taking in the data. Once it trains and builds a model, we evaluate it. If the evaluation doesn't say it's accurate enough, we then tune the model. So tuning the model might be changing the hyperparameters. So if, for instance, it's a deep neural net, we might be changing the number of layers. We might be changing more complex things as well, number of neurons, and the actual activation algorithms that we're using. At some point, the evaluation hopefully will tell us that we've got a good enough model, and then we go on to independent testing. So you can see the three different types of data that we looked at before being fed in and being used in these activities. And controlling all this is normally a development framework, which is supporting the storage of the different types of data. And it's also helping us to perform these activities of training, evaluation, and tuning so that we gradually move until we get to a stage where we get a deployed model. So what type of defects can we see here? Well, if we look on the right-hand side there, we can see a lack of explainability. One of the problems we've found with machine learning systems is that they come up with what we think are really nice results. The only trouble is we can't explain how the system came up with the result. This is especially true of deep neural nets because we can't see how they work. If we have a decision tree, we can see how the decisions are made at each stage in the tree. Whereas with a deep neural network, every neuron in the neural net runs every time we actually ask it to make a prediction. And it's very difficult to see how it comes up with a decision. If we're using on the top right there, we've got the machine learning algorithm. The machine learning algorithms, many of them are actually programmed and built by researchers. Now, most researchers doing PhD work are not familiar with software testing. So there's a fairly good chance that many of the algorithms that are out there that we reuse when we build a model are not well tested. The development frameworks are like any tools. They can contain faults, and there's also a good chance that we will misuse them to an extent. And you can see down there we've got API defects because we've got lots of different parts in these development frameworks, and therefore there's lots of interfaces, therefore lots of potentially API defects as well. So if we look at the testing types we've got for here, we can see, for instance, on the right, we've got deployment optimization testing. So once we decide that we've got a model that's accurate enough, often we don't use it in the current state. We might want our model to sit on a mobile phone. So in which case we need to optimize it to deploy to that mobile device. And if we're going to optimize it, we have to do testing to make sure that the optimization works. On the left-hand side, you can see that we've actually got a set of testing types there, which work for conventional testing as well. On the bottom left, we've got bias testing. So we're checking that the algorithm isn't biased because we can have both bias in the algorithm for instance, an algorithm that is biased to selecting the first 10 options it comes up with rather than considering all of the options. And this is in contrast to the data bias that we looked at earlier. So if we highlight the testing types that are specific to machine learning, you can see again we've got lots of new testing types. So if you're going to move into testing machine learning, these are all potentially new areas that you would have to consider. Okay, let's move into the third and final of these three areas that I identified. This is the area that is most like dynamic testing for conventional systems. So what we're going to be looking at here is we've built a machine learning model. How do we expect it to work in the real world? So we're going to typically have two steps. As we saw earlier, we get a model that is tuned, so we change the hyperparameters, evaluate it until it gets to a state where we feel it's working okay. And we have that small test data set that's independent that will tell us, hopefully, that the tuned model is working okay. So the testing done on the blue there is done on our development framework. So the equivalent of our development environment for conventional systems. And then we need to test that the deployed model is going to work in the production environment. So this is much more like system testing. Now, we might be able to do this actually on the operational environment, but a lot of the time the data is going to be include maybe personal information, in which case we're going to use sanitized data. So it won't be on the actual operational environment. It will be on a system test environment that will be as close to representative of operational as possible. So what model defect types could we have? Well, let's choose some. Bottom left there, completely specific to machine learning systems, are adversarial examples. So many of you may have heard of adversarial examples and adversarial testing. Now, one of the examples that this happens a lot with image recognition systems. And with an adversarial example, you might have an image which to a human eye looks exactly the same as another image. So it's a picture of a cat. We have a second picture of a cat, looks exactly like a cat, but we've changed just a few pixels. Those few pixels, however, are picked up by the machine learning algorithm and transform its result into a completely different result. And suddenly it's coming back with the result that it's a dog. So adversarial test examples and adversarial testing are a very specific and complex testing area that we need to look at, and especially important if we're using, for instance, machine learning systems to look at images in things like self-driving cars, because we may need to be really sure that the self-driving car can recognize, for instance, pedestrians crossing the road in all possible situations. On the top right there, you can see we've got ethical requirements missed. One of the big problems with machine learning systems and AI systems in general is that the public feel that they're going to be misused. So, for instance, although facial recognition systems are becoming more and more accurate, the public are very worried about how these systems are going to be used. So this is a quite different type of defect. And we can have biased and unfair models. So we train them perhaps with biased data. Maybe we've got a problem with the algorithm to build the model, but we end up with a model that is biased against a particular group of people. And we need to test for that, because if we put the model out there in the real world, people start using it and find that it's biased against a particular minority group, then we get really bad publicity. And obviously we need to fix that before we actually make the system live. So what types of testing can we do for model testing? Well, if we actually look at this, what we find is we've got about a 50-50 split between conventional testing techniques that can be used still for testing the models. And then we've got a number of testing techniques which are specific to machine learning. I've already talked about adversarial defects and adversarial testing, but we can have, and that's very technical, very complex. If we look under non-functional testing, we've got the ethical system testing, which is a very soft skills-based type of testing because we have to know, be very aware of all the different ethics around the system we're testing. Another area which is very technical is reward hacking testing. So with reward hacking, what happens is that our machine learning system actually starts trying to game its reward function. So when we build a system with a reward function, what we try and do is get the system to achieve rewards. So for instance, imagine we've got a robot that it does cleaning. Its reward function might be based on how much dirt it can see after it's completed its task. And we've seen systems that by trying to game this reward function have actually disabled their own vision function so that they can't see any dirt because their cameras aren't working. Another example might be a system that plays computer games, because AI systems in most areas are now better than humans at playing computer games. And we might give the system the goal of getting the highest score. And instead of actually getting good at the game, it just hacks the highest score file and gives itself the highest score. Now, testing that the system isn't doing that means that we have to create tests that are quite different from the reward function. So we have to look at how to measure the success of the systems from a completely different perspective. So what figures have we got to show us what's actually happening out there at the moment? And these are the same figures as before. So from 2020 or 2021, last year, over 1,800 respondents. And what's really sad is we can see here that only 50% of people are actually testing their ML model performance. So, and this isn't performance testing, this is actually performance in terms of accuracy. So only 50% are testing internally before they deploy the system. That means that half the systems going out there are basically not tested before we put them live, which is really sad, but a really big opportunity as well. So going back to the model I showed you earlier, we're gradually, we've moved away from just doing development with no testing. I believe that most of the industry is currently in this middle stage here, where we're doing development and testing, but nearly all of it is being done by data scientists and very little by independent testers. And I think where we're going to move to next, because we need far more trust from our users and our stakeholders, is that we're going to actually find that there's actually a specific discipline of AI testing. So it's a new specialism. And this will be performed by specialist testers who have knowledge and the skills to apply the testing types that I've been showing you over the last few slides. So how are we going to actually take this last step and move to creating this discipline? Well, things like this summit, I'm hope people are going to be talking at conferences and seminars and explaining how important this is. There's also a lot of work being done on standards for testing AI-based systems. And once we get those standards, and some already being published, then we can start looking at specialist testers actually testing AI products and maybe being able to certify those products as meeting certain levels of quality. And of course, to get the people to move who are actually qualified to perform this testing and therefore become the AI test specialists, we need a number of testing and training courses that are specific to AI and machine learning. And these are becoming available. And in fact, ISTQB already have a testing of AI-based system certification. Okay, that's my position. That's where I think we are. So if anyone's got any questions, please send them to me. Okay, thank you.
Thank you very much for this presentation. For now, we have no further questions, but of course, maybe you can tell us contact where we should ask further questions. Do you have a contact now or?
Well, I have an email address.
Okay, so.
Can you type it in or?
Yes.
Yeah, it's STU REID.
Sorry?
STU REID.
Oh, yeah.
Test at gmail.com.
Very well. Well, we will. So we will share, okay. With our viewers, and they will contact you if they have further questions. Thank you very much for attending, and have a great time in Marrakesh, and we hope to see you soon on the A4Q testing site.
Okay, thanks.
Goodbye.